Welcome. Today we are going to talk about energy pie charts, which is just one way of showing how energy is conserved. Right now I have your packet open and I am open to page 5 in your packet. What I'd like to do is just go through an example problem with you about a pie chart. What we're going to do for pie charts is we're going to start off by identifying the types of energy that you see present. So identify types of energy. And then after we've decided what types of energy we have present, then we're going to look for changes. Did something get bigger? Did something get smaller? How did the change occur? And then finally, the whole idea of a pie chart is that there's going to be the same total amount of energy each time. It's just a matter of when one gets bigger, the other has to get smaller. So for instance, if we do question number 1 here on page 5, a box slides down a frictionless ramp. That means that there's no heat. That means that there's no sound. And basically, look how it gets right back up to where it started. We're not dealing with any dissipated energy. What we want to do is say, okay, these little squiggle lines mean that it's moving. And so because we've got these squiggle lines here, and that means that it's moving, that means that there's going to be some form of kinetic energy present. And then what we also see is that the height is changing. And so we get to change a call where we want our height to be 0 anywhere we want. And I choose the lowest point of the problem to make my height equal to 0. And so because I have height above 0 at other places, whenever I have height, I'm going to use that as my identifier that I have gravitational energy. Basically what I'm looking for is identifiers. If there's height, I'm going to use that as UG. If there's motion, I'm going to use that as K. If there's some sort of a springing action or something's being stretched or compressed, I'm going to use that as spring. If I see some sort of food or fuel, I can use that as chemical. If I see wires, I'm going to use that as electrical. And so that's basically what I'm doing, is looking for those identifiers and saying, what do I see? So in question number 1, what I see is height and motion. What I also see is that A and D, there's no squiggle lines, which means that my speed is 0, which means I have no kinetic energy. What that means is that A and D, my entire pie, is going to all be gravitational. I have complete gravitational energy at A and at D. At C, though, where my height is 0, I don't have any gravitational energy. So at C, I have to say, okay, all my gravitational energy is gone. Where did it go? It still has to all be the same amount of energy present. It's just a different type. Well, it's moving there. I guess the entire thing is kinetic. Then I have to look at B and see, okay, well, it's moving and it has height. So how do I do that? Is it half and half? Really what that depends on is the height. If the height is half as much as the original, I can say that I have half my gravitational energy as I started with. And then whatever's left over has to be kinetic. So because I lost gravitational, I gained kinetic. I can see that they're both there, and they both add up to the same amount the whole time. Let's do number 2. Number 2, at location A, I see that it's moving, so I see that there's kinetic energy. It's also above the very lowest point. I'm going to call location C a height of 0, so I'm going to see that there's gravitational energy. And so when I look at A, I see that it has both kinetic and gravitational. And I'm just going to start off by saying, all right, well, half of it's gravitational and half of it's kinetic. And so when I'm at location B here, I'm going to say, okay, well, my height has gone down. So I need to make my gravitational slice of the pie smaller. I have lost height, so there is less gravitational energy. Where did that height go? Well, I think it sped up. I think that as the ball loses height, it gains speed, and that's why there's more kinetic energy here. When I get to location C, my height is 0 and my speed is 0. So it looks like I've lost all my energy, and I have to be kind of sneaky here to look for it. I see that ball is being compressed and that it's going to bounce back up to where it started. At C, my energy is all being stored as spring energy as that ball is compressed. And when I get all the way back up to D, I'm moving and I have height. And you notice that it must not have made a sound or a noise. None of my energy got dissipated during the bounce. Because on this first worksheet, basically on pages 5, 6, and 7, this says conservative forces. Conservative forces means that there are no dissipated energies present on pages 5 through 7. So you're going to continue trying to use the same logic to try to fill out the charts here. Again, go through the steps of identifying the types of energy that are present, looking for changes. Did it get higher or lower, faster or slower? But make sure it all adds up to the same total energy. What I want to show you next is how to do these same problems, but in the real world now, right? What if there is dissipated energy? How do I handle it? If there is dissipated energy, notice that the box doesn't get up as high as it started. And notice that it says that it's a rough surface here, which means yes, there's friction. Yes, there's going to be some heat, maybe some sound. And what we're going to do on these charts is we're just going to call that dissipated energy. So A is still going to have all the same gravitational energy that it had before. C is still going to be my height of 0. But friction's going to start acting on it after my initial state. So I don't ever start with dissipated energy. But from A to B, I think that it's rubbed against the surface a little bit. And so I think a little energy's been dissipated. I'm not really sure how much. So what I have to do is go to my ending condition. And at my ending condition, what I'm going to see is I'm only up about 3/4 as high as I started. So I'm going to call this 3/4 as much gravitational energy as I had at A. All the rest of this must have been dissipated. But it doesn't get dissipated all at once. Dissipated energy can only grow. As soon as I've dissipated a little bit of energy at B, that energy is gone for the rest of the time. I can't get it back. But I can dissipate a little bit more energy at C and a little bit more energy at D. Dissipated energy rose as I rub against that rough surface. And so I'm going to say at B I had a little bit of dissipated energy. At C I had a little bit more dissipated energy. And by D I've dissipated 1/4 of my energy because I no longer have the same height I did at the beginning. I know that at C my height is 0, so the rest of my energy all has to be kinetic. B is a little tricky. B I see I'm still at half my total height. So I still need to have half of my chart still be gravitational. And so really what the dissipated energy took away from was the kinetic. I'm going slower there than I used to be because of that friction. All right, let's try it one more time. This is the same starting condition as before where I said it was half gravitational and half kinetic. At B, we're bouncing. And so we know there's spring energy being stored up there. But the bounce is where the dissipation happens. The dissipated energy happens during the bounce. Each time it bounces, it's going to make a noise. Each time it bounces, it's going to give off heat. And so the bounce is what steals that energy away. So at the bounce, we're going to dissipate energy. And so what we need to do is look at our ending condition and say, oh, looks like I'm, 2/3 as high as I started. So my gravitational energy can only be 2/3 as much as what it started off to be, right here. And so whatever energy that I've lost, that energy must have been dissipated. The rest of my energy is going to be kinetic. And it looks like my kinetic is the same size each time because those squiggles are the same amount each time. So each time it's moving, I think half of it's going to be kinetic. So really what the bounce is taking away from this time is the height. Notice how after the first bounce it didn't get up as high as it started. It's almost as high as it started, but not quite. So after this first bounce, that much energy was gone. And because this much energy was gone, that happened when it bounced. So that energy, E dis, was dissipated right here, E dis, during the bounce. And now it's gone and I can't use it anymore and it has to stay gone all the way until I bounce again. When I bounce again, I can dissipate even a little bit more energy. Each bounce is where that dissipated energy is gone, and then it stays gone. Once it's dissipated, it can't come back in. And so at D, again, the height is 0, the speed is 0, the rest is all going to be spring energy. And so when we're looking at these charts where there's dissipated energy, we're going to say it happens at the bounce, it happens again at the next bounce. It didn't happen while it was in the air. It wasn't air resistance that slowed it down. It was the fact that it hit the ground that took the energy away. So you have a few problems to try on page 9 where you're going to do this. I'm going to give you a hint here for page 9. For page 9, there is going to be dissipated energy. So even though it says that there's a constant speed, what I would do for this one is I would cut it in half, and I would say that, okay, I've got half kinetic the whole time. But there is dissipated energy, there is heat, there is sound, and so you're going to see that the dissipated energy is growing throughout this problem. And so you have to figure out, where does that come from, where does that go? And then you'll do number 4 and number 5. We will talk about it when we see each other next.